So we have just seen that Maxwell equations actually express in a mathematical form some very basic observations about the relationship between fields, currents, and charges. Now, what is important is that every electromagnetic phenomenon will be always a solution of Maxwell equations. Let's see a couple of examples that will show us how from Maxwell equations we then derive some interesting results. One, for instance, is charge conservation. Now let's go back to Ampere's law, which is written here, and then we take divergence in both sides. It will look like this, and then there is some basic properties that the divergence of the curl is always zero. So we end up having this sort of relationship in which we also take into account that since here we have the divergence of D, and remembering Gauss' law, we can write this expression here. Now, we're applying now Gauss' theorem. So we apply the volume integral in both sides and apply Gauss' theorem, and we end up having this final expression. Now, when we look at this final expression, look what we have. This integral here is the net flow of J, the current density, over a closed surface. And what this is telling us is that that flow of current is related to the change of the charge inside that volume. So if this net flow is zero, that will be that this integral is zero, that time derivatives have to be zero. So if the net flow of the current over a surface is zero, then the charge inside that volume will not change. But if there is a net flow of current, either positive or negative, that means that the charge inside that volume will change, will either increase or decrease. So, and this is what is known as the charge conservation equation, which is directly derived from Maxwell equations. In a similar way, we can derive the wave equation for the electromagnetic field. The classical way to derive it is to use some vector relationship that tells us that the curl of the curl is the gradient of the divergence minus this operator here, which is the Laplacian of the vector. So in a free space, that is which charge density and current density is zero, and if we take the curl in Faraday's law and Ampere's law, and using this property, it's easily derived that the electric field and the magnetic field have to meet with these differential equations. And these differential equations are known as the wave equations, and where c is the propagation velocity of the wave, and in our case, in electromagnetics, c is 1 over the square root of mu epsilon, which in free space gives the very well-known value of 3 × 10⁸ meters per second, which is essentially the speed of light. Now, this is a very important result because it shows us that directly from Maxwell equations, we can mathematically prove the existence of electromagnetic fields, since the electric field and the magnetic field are a solution of the wave equation. Maxwell noted, was aware of this fact. Actually, he also was aware that the prediction of that propagation velocity for electromagnetic waves was showing him that, for instance, light had to be very similar in nature to electromagnetic waves, but it was not until the experiments of Henry Hertz in 1887 that he experimentally proved the existence of electromagnetic waves and that their properties were the same of light. But it's very important to realize that actually the existence of electromagnetic waves is mathematically proven and derived from Maxwell equations. Let's see with some more detail what is the meaning, what are the implications of that wave equation. Just to simplify a little bit, let us assume what we will call the one-dimensional case. The one-dimensional case means that we are assuming that the electric field is invariant along the x and y direction. It only changes along the z direction, and we're going to assume that it has a polarization along the x-axis. In that case, since the field only has one component, E sub y and E sub z is 0, and also since the field does not change along x and y, means that its space derivative is also 0. In that case, from Ampere's and Faraday laws, and remembering the mathematical expressions of the coral, we can write, they are simplified, and we have this sort of relationship. And by taking partial derivative along z and t, it's straightforward to derive this expression. This is the wave equation for the one-dimensional case, and it is very important to note that actually how the electric fields, the electric and the magnetic fields, are somehow related, interlaced between them. Notice that the space derivative of the electric field is related to the time derivative of the magnetic field, and the space derivative of the magnetic field is related to the time derivative of the electric field. So it's this interrelationship that at the end gives rise to the wave equation, to some perturbation that propagates in space and changes in time. At the end, this is the wave equation. We know that the wave equation has a general solution. This is the general solution for the wave equation. F corresponds to a function or to a wave propagation towards the positive z-axis, and G is a wave propagating towards the negative direction of the z-axis. In this animation, we can see an example or just a representation of how the wave would propagate along the z-axis. Okay. Now, of course, we are not always able to do this sort of nice animation, so usually when we plot a wave, we can do two things. Plot the field variation in a given place. Imagine this coordinate here, and this is the plot we have here. We are plotting in a given position, z equal to 10 meters, the field changes along time. Or else, we can make like a snapshot. Just for a given time, let's say 55 nanoseconds, plot how the electric field is along the z-axis. So usually we have this sort of two representations. Represent the field or represent the wave in one position a long time, or represent the field, the wave, for a given time along the position.